The universe is full of amazing and truly bizarre objects. Some of them are the result of a unique combination of many factors, while others catch one's attention with their remarkable parameters. Some of these cosmic anomalies are almost impossible to notice, while others are visible to the naked eye. And today, we invite you to go to the most unusual ones. Our journey will begin near an amazing star called Mira and its magnificent tail of gas several light years long. We will then travel to an attractive and dangerous region of our galaxy, where gravitational forces have pulled thousands of bright stars together in an ultra-dense cluster with a radius smaller than the distance between the Sun and Alpha Centauri. After traveling through most of the Milky Way, we will continue our flight among mysterious pulsars and black holes that pierce space with exceptionally powerful energy impulses. Our next stop, a mysterious magnetar, one of the most potent natural sources of magnetic fields and radiation. And after that, we will travel to the distant future, to another era in space evolution, to make acquaintance of incredible black dwarfs, the faded remnants of once great stars. Cosmo. The first in outer space. Most stars in the Milky Way slowly revolve around the center of the galaxy. Their appearance is rather recognizable and their speed is approximately the same as that of interstellar gas. Our Sun, for example, passes through the local interstellar cloud at a speed of about 25 kilometers per second. But Mira really stands out in this respect, as it whizzes through gas in interstellar space at a speed of 130 kilometers per second. As a result of such staggering propulsion, the shed material is blown back, thus forming the unique tail we can marvel at. This tail is the feature that makes Mira one of the most peculiar stars in the Cetus constellation. The tail of this star was discovered in 2007 with the help of the GALEX Orbiting Ultraviolet Space Telescope. A group of astronomers received high-quality ultraviolet light images of Mira where the tail, made up of gas and dust, can be clearly seen. At first, this tail formation rather perplexed the scientists, as the star had been under observation for over 400 years, and no tail had been spotted before. But the riddle was soon solved. Only ultraviolet images were able to reveal the tail, and only regular photos had been taken before. The length of the tail reaches 13 light-years, which is 3 times the distance from the Sun to the closest star, Proxima Centauri. As I've already mentioned, it was formed by material being shed in the course of the star's movement through space. Every 10 years, Mira sheds approximately as much material as the mass of our Earth. By estimating the length of the tail and the star's velocity, the material found at the very tip of the tail was gauged to have been dumped as long ago as about 30,000 years. As for the total mass of the material shed so far, it may be as much as 3,000 Earth masses. Marvelous as it is, the tail isn't the only feature that singles out Mira among other stars. Another feature it has is a bizarre formation that can also be seen in images beamed back from the GALEX telescope. It most likely originated as a result of Mira's speed with which it travels through the molecular cloud. A kind of bow we can see in front would have been accumulated in the many years as a result of the star's material at the front colliding with particles of interstellar gas. That makes Mira resemble a boat cutting through water, only Mira cuts through space instead. Most of the shed material is made up of atoms of hydrogen. Once shed, they gradually lose their impetus and release the energy in the form of ultraviolet rays, and it is these rays that were captured by the GALEX telescope. We know Mira as a binary pulsating variable star. In its maximal luminosity periods, it flares up to be the brightest star in its constellation, but even with its luminosity at its lowest, it can still be seen through regular binoculars. The best time for observing it from our Earth is October and November. billions of years ago this object used to be a yellow dwarf, and today Mira's stellar travels are coming to an end as it is now in one of the final stages of a star's life. Speaking about its system, it comprises two stellar companions, Mira A, a red giant, and Mira B, a white dwarf. Both objects are about 417 light-years away from our Earth, and the distance between the companions themselves is 70 astronomical units. The first component in the system is a pulsating variable star with the average apparent magnitude 3.5. Depending on the phase, however, the value may fluctuate between 10 and 2. Just to compare, the apparent magnitude of Sirius is -1.46. The mass of the system's first component is approximately 1.2 that of the Sun. Interestingly, its radius is 360 times that of the Sun. The reason for such impressive dimensions and a comparatively small mass lies in the fact that since Mira A is a red giant, its average density may be thousands of times less than that of water. Just to compare, the average density of the Sun is slightly bigger than that of water. Besides, a star hitting the red giant phase gets a massive growth spurt, and with a mass comparable to that of the Sun may in theory grow to the size of the Earth's orbit. The surface temperature on Mira A reaches 3000 degrees Kelvin. The luminosity of the star, meanwhile, is 9000 times that of the Sun. As for its supposed age, it is estimated to be 6 billion years. The red giant is not massive enough to go supernova at the end of its life cycle. Instead, it is going to expel its outer envelope and gradually turn into a white dwarf. The expanding outer envelope forms a planetary nebula, which will later on be dispersed in space around it. As for the second component, Mira B, it is a white dwarf already. As this object is located close to Mira A by space standards, it attracts material dumped from the outer layers of the red giant. In this manner, a hot accretion disk was formed around Mira B, and since matter is shed onto it at irregular intervals, Mira B is a variable star too. Its apparent magnitude fluctuates between 9.5 and 12. Thus, both components in the system are variable stars, or variables. Other stars in the universe, whose luminosity depends on physical processes taking place in their vicinity, also fall into the same category. It is important to study these objects in order to understand the nature of stellar evolution, as variable stars are more often than not at a turning point in their existence. In fact, the phenomenon of Mira is a perfect demonstration of how objects reaching some milestone or other in their life may conceal a number of great riddles. Mira's unusual features allowed scientists to use it as the prototype for a special classification for such-like objects that got the name Mira-type stars or Mira variables. Celestial objects of this variety are pulsating variable stars of late-type spectral classes, with the values for their apparent magnitudes ranging from 2.5 to 11. Mira variables are giants that shed their outer envelope in the course of several million years and eventually turn into white dwarfs. Mostly, Mira-type variables shouldn't be heavier than 2 masses of the Sun, although they may be thousands of times brighter than the Sun on account of their expanded outer layer. The pulsation of these objects occurs due to regular contraction and expansion of these stars. This also causes changes in the radius and temperature, resulting in variable luminosity. As for the chance of planets possibly hiding somewhere in these stars' orbits, only one Mira-type variable boasts an unconfirmed planetary system, R Leonis, in the Leo constellation. A star cluster is a group of stars which formed from one and the same gigantic cloud of interstellar matter. These stars are practically identical in terms of their chemical composition and age. The system they form is bound by gravity forces. Star clusters fall into either of these two categories, which are the main varieties: open and globular clusters. Open star clusters are products of stellar nursery's evolution. The latter are areas of cosmic gas where stars are actively born. That is why the clusters here are mainly comprised of young stars and great amounts of interstellar hydrogen. Gravity forces between them are comparatively feeble, which leads to an open cluster's disintegration several 100 million years after its formation, which of course is mere seconds in astronomical terms. Some of its former members still stick together in their joint movement in space, thus forming a stellar stream, while others break away from their group to become sole masters of their own destiny. Over 1,100 open star clusters have been pinpointed in our galaxy, and incidentally, it appears to be just a tiny portion of their overall count. Globular clusters are larger and denser than open ones, and consist of old and not very massive stars. The average distance between the stars there is 4 to 6 light months. As for their masses, these may reach 1 million times that of the Sun. The Milky Way contains not less than 150 star clusters of this type, and the Andromeda Galaxy over 500. Open clusters are comparatively modest in size, but the star count in some of them reaches thousands. These objects are referred to as superstar clusters. The largest of them are thought to eventually turn into globular ones. All it will take is waiting around for a few billion years or so until the most massive stars there have burned out and exploded. One of the largest superstar clusters in our galaxy is one referred to as Westerlund 1. It was spotted back in 1961 by Swedish astronomer Bengt Westerlund, but for a long while remained largely understudied, as it is quite difficult to observe. The distance from the cluster's center to the solar system has been estimated at approximately 10,000 to 15,000 light-years. Staggering though this figure may seem, Westerlund 1 is in fact one of our closest superstar clusters. That is why it is crucial to observe it, to bring our understanding of stellar evolution processes to a whole new level. The diameter of Westerlund 1 measures around 7 light-years. Astoundingly, this area, which is really tiny in astronomical terms, is literally crammed with thousands of stars with a total mass of about 63,000 solar masses. Some straightforward calculations show the distances between the major members of the cluster are just several light months. As for binary system components, they are much closer to each other than that. Due to incredible density of the stars in the cluster and the clouds of interstellar gas the stars are shrouded in, it is impossible to distinguish the exact sources of light here, as the thousands of stars this light comes from are too densely packed. This greatly interferes with observations and doesn't allow the observer to count the stars. That is why the exact star count in Westerlund 1 remains to be gauged. Among them, the following types of stars have already been pinpointed: 6 yellow hypergiants, 4 red supergiants, 24 Wolf-Rayet stars, and a supergiant with a highly peculiar emission spectrum. Supposedly, it formed on collision of 2 massive stars. In addition, there is a great number of hot blue giants and an X-ray pulsar discovered among the stars in the cluster. The pulsar is an anomalous object, a neutron star spinning with a mind-boggling speed. The binary star count is also quite high in Westerlund 1. This fact may be accounted for by the high density of the cluster's objects. All the superstar cluster's objects are posited to have formed at around one and the same time. However, depending on the type of stars, they differ in terms of their age too. To start with, according to today's theory of stellar evolution, red supergiants cannot be younger than 4 million years. Wolf-Rayet stars, on the other hand, which are in the final stage of their life cycle by definition, are remarkably numerous in the cluster. Their life expectancy is known almost never to have been over 5 million years. Thus, the age of Westerlund 1 is quite accurately estimated at a mere 4 to 5 million years, which in essence is seconds in astronomical terms. At approximately the same time it was forming, first Australopithecus and saber-toothed tigers roamed the Earth, and all that had been left of dinosaurs by then was just their fossilized remains. Mathematical modeling of the cluster's formation shows that the cluster may have contained 50 to 150 heavy stars that would have depleted their resources by now, and so would have come to the final stage of their life cycle. Given the estimates are correct, On average, there would have been supernovae every 10,000 years in the course of the past million years. As we know, the heavier a star, the faster it comes to the end of its life cycle and goes supernova, after which it leaves a black hole, neutron star or white dwarf. However, to date only one object like that has been detected. It is thought that many supermassive stars would have turned into black holes, but these are rather difficult to spot today. The superstar cluster Westerlund 1 contains one of the largest stars known today, designation Westerlund 126. Since it is rather difficult to observe it, its radius has been gauged at roughly 1,500 to 2,500 times that of the Sun. If its radius is closer to the bigger margin, Westerlund 126 may be the biggest star known to mankind. However, the radius is more likely to lie closer to the lower margin and measure slightly over 1,500 times that of the Sun. Even so, if its center were to be theoretically placed in that of the Sun, Westerlund 126 would cover all the planets, reaching as far as the orbit of Jupiter. The supergiant's luminosity is approximately 380,000 times that of the Sun, although its surface temperature is comparatively low, just around 3000 Kelvin. The star's mass hasn't been gauged yet, but today's perception of stellar evolution allows us to assume that it may be around 20 solar masses. Another unusual object in the cluster is a magnetar with a name like a tongue twister. It is also the most powerful source of X-ray radiation in that area of space. Located approximately 16,000 light-years from the Sun, it is a neutron star, whose rotation period is about 10 seconds. Incidentally, this is rather slow in comparison to other objects of this class. Those rotate several times a second. Given that all the stars in the cluster formed at around one and the same time, it would have taken the star that was the progenitor of this magnetar just 5 million years to deplete its thermonuclear fuel. This means that when it was born, its mass should have been not less than 40 solar masses. However, in that case, it should have left a black hole rather than a neutron star after going supernova. It transpires that the progenitor star had to unaccountably lose up to 95% of its mass before going supernova. One of the possible answers to this riddle may lie in the fact that the object may have originated from a binary star rather than a single one. By spinning around their common mass center at an astounding rate, the system's components had a chance of actively exchanging material. At some point, the supernova would have scattered most of this material in the space around it, while the second component would have been ejected from the system. The star Westerlund 1.5, which is located comparatively close to the magnetar, may well have been that very component, although it is not certain. Unfortunately, chances of discovering any planets in the superstar cluster Westerlund 1 are thin. First of all, the stars the cluster is comprised of are too young for any planets to form in their environs. This curious process takes hundreds of millions of years at the very least. Secondly, even billions of years later, when the cluster supposedly turns into a globular one, it is hardly worthwhile to anticipate any objects to be born there that would potentially be capable of sustaining life. The close proximity of large and heavy stars makes the potential planet's orbits unstable. Moreover, in certain circumstances, a massive neighbor relatively close to a star system may actually destroy it completely. Besides, thousands of active stars concentrated in a small area of space create a remarkably powerful radiation background. Frequent flares of supernovae occurring in this crammed space may cause harmful gamma-ray bursts which destroy any life on a planet's surface. Chances are that even if mankind finds a way to cover interstellar distances, clusters will still remain deadly areas for quite a while. As a rule, microquasars are X-ray binaries, that is, stellar systems made up of two components. One of them is a regular star similar to our Sun. The other component is a compact object like a black hole or a neutron star. Matter in such microquasars is constantly in the process of accumulating in the compact object, which is accompanied by occasional outflows of matter at great speeds. These outflows are known as jets, and the nature of these jets reminds one of processes taking place in regular quasars. Now, it is not a regular occurrence in ordinary quasars. Meanwhile, as the mass of a microquasar is smaller than that of an ordinary quasar, jets may originate here practically on a daily basis. The principal difference between microquasars and ordinary quasars is in their mass and the frequency of matter outflows. For example, the mass of the compact components in microquasars is considerably smaller than the mass of those in regular quasars. It is just several solar masses. Just to compare, the average mass of a supermassive black hole in the center of a quasar may be approximately as much as 100 million solar masses. As for the mass of the black hole likely to be found in the center of SS433, it must be just a few dozen solar masses. The accretion disk of a microquasar is intensely luminescent, with emissions in the optical and X-ray bands. A regular quasar is an astronomical body boasting the highest luminosity among other objects in the observable universe. According to contemporary scientific views, these celestial bodies are active cores of galaxies where a supermassive black hole sucks in matter all around it, thus forming an accretion disk. As for the disk itself, it is a source of very powerful luminosity. Just to give you an idea, its luminosity may sometimes be hundreds of times as intense as that of all stars in a galaxy like ours combined. To date, over 200,000 quasars have been identified. We're able to observe some of these quasars in the sky even without using a telescope, and so the rate of discovering new objects of one or the other category is another principal parameter by which regular quasars and microquasars differ. If we look at the list of known microquasars, it contains just a few entries so far. The first microquasar was discovered back in 1978, when a source of unusual radio and X-ray emissions was detected by two astronomers from the University of Cambridge as they were looking for debris left over from supernovae. Detected in the constellation Aquila, this source was later dubbed SS433. The object under scrutiny is an eclipsing X-ray binary system. One of its components is likely to be a black hole. As for the second component, it is a star of spectral type A. That is, a main sequence dwarf star of a whitish hue. It is assumed that this star's mass is 10 to 30 times that of our Sun. And more likely than not, the dwarf used to be considerably heavier in the earlier stages of its existence. Its surface temperature is thought to be anything from 7,000 to 11,500 degrees Kelvin. This temperature range is typical for stars of this type. It is actually its temperature that gives the star its pale yellow tint. In fact, if we look at the stars closest to the Sun, then Sirius, Altair and Vega fall into the same class as this star. SS433 is located within the supernova remnant W50, sometimes also called the Manatee Nebula. The age of this nebula is estimated at approximately 20,000 years, and the distance between the nebula and the Earth measures about 18,000 light-years. The jets from SS433 distort the clouds surrounding the W50 nebula. According to a certain theory, the W50 nebula and the microquasar SS433 are actually related, and came to be as a result of one and the same supernova event, which supposedly took place around 20,000 years ago. It takes either of the two objects in the system 13.1 days to orbit the common mass center. In fact, the way the SS433 system works is quite exciting, with both components constantly interacting with each other. Matter from the second component, that is the regular star, flows to the first component, or the primary, supposedly a black hole, thus forming an accretion disk around it. As it spirals, the matter heats up to extreme temperatures and emits X-rays. Some part of this matter leaves the system in two jets at the rate of approximately 26% of the speed of light. That is 79,000 kilometers per second. In 2019, thanks to the ALMA observatory, astronomers managed to get detailed images of SS-433. It was clear from the emission structure that the microquasars' jets themselves are rather narrow and their shape is irregular and has nodes. Further studies of the object showed that the shape of the jets is distorted as a result of precession, that is, a process when the jets slowly rotate on their axis as they spiral. The diameter of either of the two jets ejected from the microquasar in two opposite directions measures approximately 5,000 times the diameter of the Solar System. As SS-433 is relatively close to the Earth, it is particularly valuable to scientists studying the phenomenon of microquasars. Images beamed back by the ALMA observatory showed its jets for the first time, and it also helped establish that the direction these jets point at is never the same. Just like a top, the spinning toy gradually slows down, they too rotate on their axis, which is perpendicular to the plane of the accretion disk. The ALMA images boasted another outstanding feature. The shape of SS-433 was predicted in fine detail thanks to spectroscopic measurements that had been done in 2018 using the Global Jet Watch telescopes. And so the actual shape largely corresponds to the new images, where SS-433 is really seen to have a shape reminding one of a corkscrew. It isn't a rare occasion when jets like that originate here or there in the universe. As a rule, jets of plasma, also known as relativistic jets, are spewed out of the centers of active galaxies, quasars and radio galaxies. When this occurs, there are usually two jets as such, pointing in the opposite directions. And this is exactly what we can observe in the case of SS-433. Today, the phenomenon of jets like that wants deeper studying. It is believed that jets originate following the interaction between magnetic fields and the accretion disk around a black hole or a neutron star. As for their size, it may be staggeringly enormous. In the case of the radio galaxy 3C120, for example, the jet stretches for at least several kiloparsecs away from its source. It is highly probable that in the future the regular star in the SS-433 system will shed its outer layer completely as a result of the influence of the compact object. Its core, meanwhile, will remain hot, and thus the star will qualify to be called a hot subdwarf. Later, the star is to be gradually sucked in by the black hole, and sooner or later, after this process is completed, the SS-433 system will assume a classical look. It will comprise just the compact object. It goes without saying that to detect a celestial object that absorbs all light shed on it is a challenging task, to say the least. That is why there are not that many confirmed black hole candidates today. Still, mathematical modeling shows that their number in our galaxy may reach 100 million. This may seem an incredibly big number, but since there are 200 to 400 billion stars in the Milky Way, it makes us realize that in all these expanses, black holes are objects one doesn't come across that much. In one of our previous videos on the topic, we mentioned that a star, the progenitor of a black hole, has to have a mass of at least 18 to 20 solar masses. Only this will ensure a powerful enough supernova to compress the scorching hot core of the star to an exceptionally dense clump of material. After this has occurred, nothing will be able to stand up to the object's gravity force and escape beyond the boundaries of a conventional sphere predefined by the so-called Schwarzschild radius. What used to be a star transforms into a bizarre object with an inner makeup that would defy description by the physical laws we're familiar with. The object, referred to as A0620-00 or V616, is one of the black holes closest to our Earth that we know of. It lies 3,300 light-years away from our planet and forms part of a binary star in the constellation Monoceros. The other object in the system is an orange dwarf with a mass half that of the Sun. Every 7.75 hours, it completes a full orbit around an invisible object of unknown nature. Estimates show the mass of this invisible object to be around 6.6 times that of the Sun. It is admittedly too much for a neutron star. This leads one to believe that the bizarre invisible object is more likely than not a black hole. In addition to getting deformed and elongated by the more massive neighbor's gravity, the orange dwarf is also getting stripped of the outer layers of stellar matter. Spiraling streams of scorching gas gradually flow to the black hole and form a bright accretion disk. It is thanks to this dazzling disk that the black hole was detected. There are at least several dozen stars in the environs of V616, some of which almost certainly have their own planetary systems. It is highly likely that in the future, one of these stars will get dangerously close to the black hole and as a result will be sucked in by the object's insane gravity. This unfortunate star will have no choice, and in this case, the same slow demise is eventually awaiting the black hole's new companion as that of its current one. The process of interaction of a black hole with other objects largely depends on their mass ratio. The smaller the distance between them and the more massive the black hole, the stronger the influence of its tidal forces over its companion. The star may be deformed by them and get stretched towards the system's common mass center. They can also form channels that would carry stellar matter closer to the black hole, adding up to its accretion disk. If the tidal forces happen to be strong enough, they may well destroy the object that is being sucked in by turning it into a fiery ring. It is assumed that there may be planets orbiting a black hole, just as if it were a regular star. In contrast to a widespread opinion, black holes are actually not able to suck in all objects around them indiscriminately. From the point of view of gravitation, in astronomical terms they behave just like any star with the same mass. That is why, incredibly though it may seem, a black hole may well have a stable planetary system. There are several ways for them to form. Firstly, new celestial objects may originate in a nebula of gas and dust that is formed after a supernova. Influenced by gravitation, they first form clumps of material that collide with each other and attract cosmic dust. As a result, they eventually turn into planets and satellites, as well as large numbers of small celestial objects, like asteroids and comets. The radiation of the black hole's accretion disk may be powerful enough to warm them, and even melt ice on their surfaces. Hypothetically, a planetary system like that could be favorable enough for life to originate and, with any luck, evolve. Secondly, when a black hole captures and destroys another planetary system, some of its objects may choose to take up stable orbital positions around their new host. Of course, this makeover would bring about dramatic changes on the celestial object's surfaces. Thus, an ice giant may transform into an ocean planet, and a gas giant may lose almost all of its hydrogen and turn into a Chthonian planet. Thirdly, space wanderers like rogue planets or interstellar asteroids may also be ensnared by the massive object's gravity. Even though systems like that have not yet been discovered in practice, there is no reason to suppose they are non-existent. If, on the other hand, a planet is too close to the system's center, and the black hole is massive enough, other factors come into play. A scorching hot stream of material forming the accretion disk will strip the celestial object of its atmosphere, and its friction will slow it down and pull it still closer to the black hole. Eventually, extremely powerful tidal forces will rip the planet to tiny shreds. The debris will be pulled into the accretion disk and gradually melt in the hot gas around. In the end, they will inevitably get swallowed up by the black hole and in essence become part of it. It is posited that there are three main types of black holes to be found in the universe that are different first and foremost in terms of their mass. The first type can be found in the center of most spiral galaxies. These are gargantuan black holes with masses reaching several billion solar masses. The density of matter in the central part of a galaxy is generally extremely high, which is the reason why there originate a big number of large and bright stars quite closely packed. As they rapidly burn out, they transform into black holes, which in their turn rapidly grow and often merge with each other. As a result, supermassive objects are born, which are surrounded with giant accretion disks made of scorching hot material. They illumine space so brightly that it makes them seen from billions of light years away, even if their galaxy is completely unobservable to us. These objects are known as quasars. The second type is much more widespread, but at the same time, black holes like these are not that easily detectable. Their masses are close to those of stars, and they form out of large stars at the end of the latter's life cycle. By devouring other celestial bodies and interstellar gas, these objects gradually gain in size and eventually turn into intermediate-mass black holes. They can also merge together, which generates gravity waves that distort space many light years around. The third type is the hypothetical primary black holes. Their existence has been inferred from today's theory of universe's origins and evolution. Fluctuations in matter that filled space in its early stages of evolution may have been favorable for black holes of infinitely small size to originate. It should be mentioned that according to estimates, the smaller an object of this type, the faster it evaporates, and at the end of its life cycle it turns into a tremendously powerful electromagnetic impulse. Modeling shows that primary black holes with masses around 10 to the power of 12 kilograms are supposed to be flaring up sometime around now, but to date, no such event has been registered yet. According to a certain hypothesis, a microscopic black hole may form on collision of extra-high-energy elementary particles. This variety is referred to as quantum black holes. Still, the conditions necessary for such an event to happen are impossible to be reproduced in lab conditions, and estimated life expectancy of these hypothetical objects is so small that it can hardly be measured with today's latest and most advanced methods. That is why quantum black holes still officially exist only in theory. July 1967. A series of pulses was detected with the help of a radio telescope at Cambridge University by a postgraduate Jocelyn Bell. They emanated from a pulsar as yet unknown at the time, and the results of the observations were kept secret for several months. The object was initially designated LGM-1, which stood for Little Green Men. The name was given following the assumption that these perfectly regular pulses were not a natural phenomenon but signals of artificial origin, supposedly transmitted by an alien civilization. Besides, the team of scientists under Jocelyn Bell discovered 3 other sources of similar signals. The phenomenon took 7 years to investigate, and the thesis advisor of Jocelyn Bell's team was later awarded the Nobel Prize for studying this celestial body, which was subsequently dubbed PSR B1919+21. This pulsar was the first registered phenomenon of its kind. Its source was to be discovered several years later in the constellation Vulpecula, or Little Fox, 2,283 light-years from the Earth. Information about PSR B1919+21 was made public in February 1968, and by 1969 the number of detected pulses of this kind reached 27, and the term pulsar was coined as the official name for these objects. The first discovered source of this signal was the object dubbed PO943. It was spotted by Soviet astronomers in the Leo constellation. One of the most widespread assumptions at the time regarding this discovery was that all pulsars were in fact ultra-powerful radio beacons of extraterrestrial civilizations, and the pulsating signals remind one of a lighthouse twinkling in the night. However, it wasn't long before astronomers agreed that the regular signals were most likely emanated by neutron stars. Today, it is posited that these impulses originate as a result of a neutron star's spinning, and are in fact thin beams of radio waves. They are detected by the observer at precise regular intervals, which accounts for the pulsed appearance of this emission. Approximately 1,790 pulsars had been discovered by 2008. All of them were powerful sources of impulse radio emissions in space. As for the pulsars closest to us, they are located several dozen light-years away from the Sun. After pulsars were first detected, Other pulsating sources of similar nature were registered by astronomers. They were described as powerful flares of regular intermittent X-ray emissions. Thus they got their name, X-ray pulsars. X-ray pulsars are also highly magnetized neutron stars, but unlike radio pulsars, which use their own rotational energy, X-ray pulsars are powered by accretion disks. An accretion disk is formed from material captured from the companion star, with the latter eventually becoming a white dwarf with all of its resources depleted. Thus, the mass and spin rate of X-ray pulsars gradually build up during the course of their revolution. As for radio pulsars, they on the contrary slow down as time goes by. For example, the average radio pulsar completes one rotation within the period from several seconds to several tenths of a second, with X-ray pulsars completing hundreds of rotations within the same time period. One of celestial bodies of this kind was discovered quite recently, and it is located rather close to our system. The object was dubbed J1023+0038, and its source caught astronomers' eye as recently as at the beginning of the 21st century. However, its pulses reached the Earth only in 2017. This was the first ever millisecond optical pulsar to be discovered. In essence, such celestial bodies are neutron stars as well. With a rotation period ranging from 1 to 10 milliseconds, the spin rate of these pulsars is several times that of regular pulsars. They form part of binary systems, and their spin rate increases to incredible speeds as the direct result of the pulsar pulling material from the gaseous disk produced by its companion star of a smaller mass. It should be noted that when a neutron star is in its active accretion phase, we see it as a source of X-rays. When the rate at which it pulls the material drops, bright pulsed radiation can be seen in the radio and gamma spectra. To date, a few more pulsars of this transitional kind are known to science, which fluctuate between the X-ray and radio spectra in a similar manner. However, it was the first ever transitional optical pulsar with a spin rate of this intensity discovered by scientists. The rotation period of J1023+0038 is 1.69 milliseconds, which is 0.00169 of a second. The object itself is 4,500 light-years away from us. The mass of its companion star is 0.2 that of the Sun. It takes the pulsar 4.45 hours to orbit its companion star once. To date, the properties of J1023+0038 have not been investigated in detail, although it is likely to be a not very massive neutron star. Although the object was initially considered to be a radio pulsar, in 2013 scientists noticed that its impulses regularly subsided and it was known to flare up in the X-ray spectrum. According to scientists, this phenomenon may be accounted for by the fact that the pulsar was at the moment in between the phases, which looks like the following. Radio emissions occur when material from the companion star is pulled to the pulsar, but star wind does not allow material to form an accretion disk. That is why the gas cannot heat up much and looks brighter in the radio spectrum. In the second phase, the stream of material from the companion of J1023+0038 gets stronger and forms an accretion disk around the pulsar. The disk is in fact the source of observable X-ray emissions. It wasn't long before millisecond pulsating was detected in the optical band of J1023+0038. As testified by earlier observations carried out with the help of the Swift X-ray telescope, the neutron star was surrounded by an accretion disk at the time. According to those in charge of the studies, the pulsar may have started to flare up in the optical band due to electrons in its magnetosphere when these electrons' speed was close to the speed of light. In the future, astrophysicists plan to conduct additional observations to study processes taking place within this binary system. And now to the object of the kind located furthest away from us that is known to science. It is NGC 5907X1, a celestial body which is also the brightest of all pulsars discovered by now. Spotted in 2017, this pulsar is an ultra-bright X-ray source. Shockingly, it releases as much energy in one rotation period as the Sun produces in 3.5 years. Earlier, astrophysicists believed these ultra-bright X-ray sources to be black holes. However, after the discovery of NGC 5907X1, it became known that they may turn out to be pulsars too. The object is located approximately 50 million light-years away from our Sun. As for its spin rate, it is variable. For example, in 2003, the rotation period of the pulsar was 1.43 seconds, whereas in 2014 it dropped to 1.13 seconds. Just to compare, if our Earth were to be able to change its rotation speed in the same manner, a day on our planet would last just 19 hours. Modern astrophysical models cannot account for the intense luminosity of NGC 5907X1, although scientists believe it to have something to do with a powerful multipolar magnetic field that may be concealed within the pulsar. It will take even more complex studies to find out the reason for the emission of such staggering amounts of energy. Mankind has come across some extremely powerful radiation that reached us from deep space several times in the last 50 years. But as often is the case with space discoveries, the source was slow in being detected by astrophysicists. 1979. 3 US Vela satellites monitoring nuclear tests on the Earth detected an unusual gamma-ray flare. 1992, astrophysicists assumed that there was a celestial object out there not known to science with a huge electromagnetic radiation coefficient. 1998, a gamma-ray flare in the constellation Aquila. A number of measuring devices registered an unaccountable anomaly with its source located tens of thousands of light-years away from us. 2004, all telescopes in the world were for a short time dazzled. Less than a second later, every cubic centimeter in the solar system experienced a wave of gamma-ray radiation, the most massive burst in the entire history of observations. And today we're closer than ever to finally putting our finger on the nature of this discovery. A magnetar is a neutron star with an exceptionally powerful magnetic field of about 10 to the power of 13 teslas, which in essence is trillions of times that of the electromagnetic radiation on the Earth. It is also one of the rarest and really most dangerous phenomena ever encountered by mankind. When a supermassive star is on the point of dying, a supernova occurs. Among the multiple scenarios of what may take place after that, only one may lead to the star becoming a magnetar after the supernova. Many of you would have heard about the Russian roulette at least once in your lives. According to the rules, only one cartridge is put in the revolver's cylinder. The chance of producing a shot after you have spun the cylinder is rather small. However, when it does happen, the consequences are truly mind-blowing. Be it as it may, scientists are still at odds over what exactly this scenario would look like. According to the first theory, it's the inner energy of the star and its rotational energy that influence the formation of a magnetar. If a neutron star is formed at the time of fast rotation, the inner energy of this star as well as its rotational energy, which is of great significance in the first several seconds, all create a powerful magnetic field. This process is known to science as a dynamo mechanism. But there is another theory as well. After the accretion process, the magnetar may be able to receive energy from another star. Scientists have discovered a magnetar which is on an escape trajectory from our galaxy. Most moving stars we know set off on their trajectories as a result of supernovae in binary systems. This means that the accretion process takes place between the two stars with a common mass center in a binary system. Matter from one star gradually flows to the other. In this case, this is the source of energy for a potential magnetar. Something similar happens with a basketball spinning around the edge of the basket. Sooner or later it is going to fall, but it's the spinning process that predefines the direction of the fall. Magnetars spin on their axes extremely fast, with a speed varying between tens and thousands of times per second. At the same time, their dimensions are record small. As a rule, the diameter of a magnetar reaches a measly 20 to 30 kilometers. Just to compare, the diameter of the Moon equals 3,474 kilometers. That is about 173 times that of the average magnetar. The mass, however, is a completely different matter. A magnetar with a diameter of 15 kilometers will be significantly heavier than our Sun, despite the dimensions. It is its staggeringly powerful density of the interior that is the reason for its high magnetic radiation. For instance, 1E1048.1-5937 is an anomalous X-ray pulsar located 9,000 light-years away in the constellation Carina. The star the magnetar evolved from had the mass 30 to 40 times that of our Sun. The matter in these stars is dense to such a point that a fountain pen cap would weigh billions of tons, and a human would be torn to bits within a matter of seconds after landing on the star's surface. Several years ago, astronomers from NASA managed to register a phenomenon which came to be known as a starquake. Thanks to the Fermi Gamma Ray Space Telescope, scientists received data about intense X-ray bursts. Their source was magnetar SGR J1550-5418. The magnetic field of this star is so powerful that from time to time its crust bursts with vast amounts of energy released through the crack. Such starquakes are the source of pulsed electric current. In theory, if a magnetar of this kind at its most active were to find itself within the boundaries of the solar system, we wouldn't as much as notice the threat, as the ozone layer of the Earth, together with all organic life forms, would be wiped off within a matter of a few hundredths of a second. Fortunately, however, the magnetar closest to us is a safe enough distance away. A magnetar is hard to approach not only due to the gravitational properties of its core and energy flares at the time of a starquake. When a magnetar is in its stable condition, its magnetic field is able to mess with electric devices hundreds of thousands of kilometers away, and within the radius of 1,000 kilometers, any object would be reduced to atoms. In order to systematize the difference in their radiation, scientists decided to divide magnetars into two varieties by using abbreviations. Rather than the full names, you will see these in any astronomical catalog. SGR, soft gamma repeater, and DXP, anomalous X-ray pulsar. In essence, SGR and DXP are different phases in the life of one and the same object. According to scientists, a magnetar exists as an SGR pulsar for the first 10,000 years. That is, it's a pulsar visible in regular light and repeatedly emitting bursts of soft gamma rays. As time goes by, it exhausts its properties and recedes into the invisible spectrum, when it can be seen to us only in the X-ray range, as an AXP. According to different sources, today among billions of neutron stars, the number of known potential magnetars ranges from 30 to 150. There are about 12 of them in the Milky Way, with the closest under the name 1E2259+586 being about 4 kiloparsecs or 13,000 light-years away from our Earth. The magnetar is a soft gamma repeater, and if a starquake were to take place on its surface, it would affect us only by some slight changes in the top layers of the ionosphere. Due to their small dimensions and remoteness relative to the Earth, magnetars cannot be observed through regular amateur telescopes. The method of infrared or X-ray scanning of the sky is usually employed to observe them. Nevertheless, thanks to their active magnetic field emission and radiation, these stars are much easier to detect with the use of various instruments. This is exactly what took place several years ago, in 2013. Astronomers claimed to have discovered a magnetar in close proximity to a supermassive black hole right in the middle of the Milky Way. The star was detected thanks to several orbital telescopes, including the Chandra X-ray Space Observatory. SGR 1745-2900 is only 0.3 light-years away from the edge of the black hole. And to date, it remains the only neutron star to have been discovered in close proximity to an object of this scale. SGR 1745-2900 has been observed by scientists ever since its discovery. Several years ago, the level of its X-ray radiation was proclaimed to be significantly lower than that of the stars of this category. The news prompted numerous debates. Can these changes have been caused by the black hole in the star's environs? After 2 years of observing SGR 1745-2900, astrophysicists came to the conclusion that, all things considered, the distance of 0.3 light-years is insufficient for any interaction in the magnetic or gravitational field to take place between the black hole and the magnetar after all. The reason is likely to lurk elsewhere. A magnetar's lifespan is quite short, just about 1 million years, and it's quite natural for its magnetic field to gradually die down throughout the star's existence. Some scientists assume that these processes may be the reason for the change of the star's status. In this case, magnetars can switch their category, flare up more frequently or less often, deplete the stock of the matter, and thus go from the category of SGR to the category of AXP. In its autumn years, a former magnetar that managed to survive the dissipation of its magnetic field may even become quite a different kind of star, namely a thermally emitting neutron star. So far, just about 7 objects of the kind are known to science. For their number, this group has been dubbed the Magnificent Seven, and each of them may once have been one of the most dangerous objects of deep space. But in order to establish that, it will take us long years, further technological advancements, and dedicated people willing to devote their lives to searching for solutions to the most dangerous and incredible mysteries of the universe. The term stellar evolution in astronomy refers to the sequence of changes that a star undergoes throughout its entire life. This process largely depends on the object's initial mass, and may take anything from several million to tens of billions of years. As a rule, a star originates from a cloud of cold, low-pressure interstellar gas. Due to gravitational instability, the cloud compresses and eventually slowly assumes a spherical shape. During the compression process, the gravitational field energy is transformed into heat and radiation, with the temperature of the young star gradually going up. The duration of this stage depends directly on the star's initial mass. With the heaviest stars, it may take about 100,000 years, and with the lightest ones, the phase may last up to several billion years. Our Sun's mass, for instance, is comparatively small, and so it remained in this first phase for approximately 110 million years. In the next phase, after a sufficiently high temperature has been reached at the core, thermonuclear fusion takes place inside the star and the compression ceases. After this, the processes taking place at the core become the star's only energy source, and thus a young star, which is also called a protostar, becomes a main sequence star. This is the starting point for calculating a star's age, as this phase accounts for approximately 90% of its life cycle. Our Sun, for example, will remain in the main sequence stage for approximately 11.5 billion years. When a star enters its main sequence stage, its chemical composition is still very close to interstellar environment and is 91% hydrogen. At the same time, the process of hydrogen transforming into helium is constantly in progress inside the star. As a result, the core compresses and gains in density, which gradually increases the rate of chemical reactions. It leads to noticeable changes in the star's properties. For example, the luminosity of our Sun in the main sequence stage accounted for only 70% of its luminosity today. By the time this stage is over, the luminosity is going to be 2.2 times that of today. It should be mentioned that not all stars make it to the main sequence stage. The exceptions known to science today are referred to as cold and hot subdwarfs. These objects are very similar to main sequence stars, but they do differ from them. Thus, by contrast, subdwarfs are not rich in heavy elements and are not so luminous. The final phase for main sequence stars also depends on their mass. Generally, a star either discards its outer coat, thus becoming a white dwarf, or goes supernova to later become a neutron star or a black hole. A supernova is a phenomenon when a star's luminosity dramatically intensifies, with great amounts of energy released during the process. After that, the flare slowly fades. This explosion is accompanied by emissions of great amounts of matter from the outer coat. The remaining matter in the core of the star gone supernova generally forms a compact object, either a neutron star or a black hole. Apart from everything else, the matter released in the course of a supernova event contains products of thermonuclear synthesis. It is thanks to these elements that the universe is able to evolutionize chemistry-wise. If a star's mass doesn't quite reach 8 sun masses, however, this main sequence star will end up being a white dwarf. That is, an object which is a hot celestial body of small dimensions and a high density. For instance, in the case with our Sun, when the time comes for it to go through this phase, it is going to become 100 times smaller than it is now. White dwarfs do not generate energy and are luminous only on account of their high temperature. Even though the hottest white dwarf's surfaces may be as scorching as 70,000 kelvins, due to their small size, their luminosity is not that great. As for their average density, it is almost 1,000,000 times that of the regular density of main sequence stars. These objects consist for the most part of a plasma of nuclei and electrons, and are completely devoid of thermonuclear energy sources, which is why they gradually cool off and assume a red hue. Sirius B is the closest white dwarf to us that we currently know of, and it is 8.6 light-years away. This object's mass is give or take that of the Sun and is considered to be one of the most massive white dwarfs known today. Its volume is 1/1,000,000th of that of the Sun, and its dimensions are identical to those of our Earth. Sirius B is believed to have become a white dwarf approximately 120 million years ago, with the initial mass of the star in its main sequence phase having been 5 sun masses. Today, it is posited that these objects account for 3 to 10% of the overall stellar population of our galaxy according to different estimates. Over 97% of the stars known today are eventually destined to become white dwarfs. As time goes by, these objects are bound to cool off and fade. Eventually, all celestial bodies of this variety will become black dwarfs, which implies that they will completely cease to emit any visible light. This process takes scores of billions of years. That is why to date science hasn't had a chance to observe any of these objects. The universe is considered to be too young to have produced any black dwarfs at this point, but scientists have already managed to spot objects quite similar to them, whose temperature has gone down lower than 4,000 kelvins. These objects are white dwarfs WD 0346+246 and SDSS J110-217. A black dwarf is what most stars look like at the final stage of their evolution. Its mass is quite identical to that of a white dwarf. According to today's models demonstrating cooling of these bodies, white dwarfs formed in the course of the evolution of the first generation of stars are supposed to have a temperature of approximately 3,200 kelvins and to appear as rather dim objects. For all we know, these celestial bodies could be part of the universe's hidden mass components. For a white dwarf to cool off to the temperature as low as 5 kelvins, it may take approximately 1 quadrillion years. In theory, when black dwarfs cool off completely, the process of dark matter annihilation becomes very important for their existence. This phenomenon hasn't been directly observed in the universe yet, although it is thought that in the course of annihilation, particles of dark matter will form ordinary photons and emit light visible through a telescope. Without allowing for this phenomenon, black dwarfs are believed to cool off and fade to the point where their temperature equals the background temperature of the universe. However, in theory, thanks to the energy derived from dark matter annihilation, black dwarfs may well continue to radiate energy for a considerably longer period, and thus enjoy their luminosity longer. The process of dark matter annihilation in these objects is thought to continue for as long as the galactic halo remains whole, and that means for over a septillion years. After that, dark matter annihilation gradually ceases, and only then will black dwarfs cool off completely. It is likely that mankind will never be able to discover objects of this kind, as the main period of their life takes place in the phase in the life of our universe which will come after the one we're in at the moment. The period we live in is a star epoch. That is the period where stars are still born quite actively. This epoch will last up until the point when the galaxies will deplete all of their interstellar gas. After that, it will be the turn of low-mass stars like our Sun to fade. Following that, a long period of disintegration will begin, when white, brown and black dwarfs are the main objects populating the universe. At the next stage, the epoch of black holes, all matter in the universe will be transformed into elementary or subatomic particles, with the remaining black dwarfs getting sucked in by black holes or completely disintegrating. The final stage in the life of the universe is supposed to be the epoch of eternal darkness, where there won't be any energy sources whatsoever in space. The overall temperature in the universe will reach absolute zero. Space will gradually expand, and in the light of the last and rare black holes, in about 1 Gugol years, our world will come to its gloomy end. Of course, every cosmic object is unique in its own way. We see only a small part of the great diversity of the universe, because countless stars are dimmed long before the emergence of mankind, and the same great number of them have not yet flared up. The mysteries of the great cosmos are truly inexhaustible, which means that there are many more amazing discoveries ahead of us. And let's keep in touch.